Well, let's talk about the idea of linear independence of vectors. So we'll talk about what that means for a set of vectors to be linearly independent, and then knowing that, how do we check if a set of vectors is linearly independent? And what do you think the odds are that we will boil this down to solving a system of linear equations? I think the odds are pretty high. So here is a pile of vectors. There's n of them. They could be geometric vectors or matrices or polynomials, any kind of vectors that we have in a vector space. We're going to list off several things that all mean the same thing, that all identify whether these things are linearly independent. The first hook we get into it is that the vectors are linearly independent if none of them is in the span of the others. Now we know what that means. That means that none of them is a linear combination of the others, which means there's no way that we can take this pile of vectors, set one of them aside, and write it as a linear combination of the others. Because if we can do that, then we could arrange it so a total linear combination of all of them would cancel out, right? If one of them is a linear combination of the others, then its coefficient could essentially be the canceling term for all of the rest. And we don't want that to happen. We want these things to not have the ability to essentially cancel themselves out. And so linear independence means there is no way for a linear combination of the vectors to cancel out and return the zero vector unless you're multiplying all those vectors by 0 in the first place. So the only way for the linear combination to return 0 is that the individual multiples a1, a2, and down the line all happen to be 0 anyway. So are these three vectors linearly independent? Well, here's how we're going to find out. We're going to build a linear combination of those three vectors and see what it takes for that linear combination to return the 0 vector. This is a homogeneous system of equations. Knowing how those work, that means just generally for a homogeneous system, you're either going to get infinitely many solutions or you're going to get one unique solution that is the trivial solution, that is zeros for all of your unknowns anyway. And so this will help us decide whether or not the vectors are linearly independent. If we do get that unique trivial solution, then the vectors are linearly independent. And if we discover that there are infinitely many ways for this equation to work out, then those vectors are linearly dependent. So this is how that breaks down. Here is that linear combination producing the 0 vector. What does that take? Well, it takes the collection of first components to produce 0, the collection of second components to produce 0, and similarly the third components have to lead to a 0. So 3 equations in 3 unknowns. You know how to solve it. We're skipping a lot of the details. If we build the augmented coefficient matrix for this homogeneous system and then reduce it, we get an augmented coefficient matrix with the identity matrix on the left side, which means the solutions are a1, a2, and a3 all being 0, and therefore these vectors are linearly independent. Let's check if these polynomials are linearly independent. Again, to do that, we're going to build a linear combination of them and ask, what does it take for this to return the 0 vector in this space? Now in this space, the 0 vector would be 0x squared plus 0x plus 0, right, which is just 0. So here's what the linear combination looks like. To see what it takes for that to make 0, we have to collect the coefficients of x squared, x, and the constant term and make sure all of them turn into 0. So again, a system of 3 equations in 3 unknowns. The augmented coefficient matrix for this system and its reduction is right here. And again, a1 equals 0, a2 equals 0, a3 equals 0. We do have the trivial solution to our system of equations. The polynomials are linearly independent. Then as a final example, here's 3 matrices. Are they linearly independent? Well, we're going to check. We're going to build their linear combination. We're going to ask, what does it take for that to return the 0 vector? Either we'll find infinitely many ways, or we will find that the only way that this can happen is that a1, a2, and a3 themselves have to be 0. When that happens, we have linear independence. So to make this work out, we need to match 4 component values from the left and the right. So that's going to generate 4 equations in 3 unknowns. So we build the total upper left entry on the left-hand side, for example, that's A1 minus 2A2 minus 3A3. That will have to produce a 0 on the right-hand side, and so on for the rest. So that's 4 equations, 1 per entry, matching the left to the right. The coefficient matrix of that system of equations and its reduction look like this. And this reduction's turned out a little different than the other two. This reduction is telling us that we actually have an infinite number of solutions. Therefore, the matrices are not linearly independent. So those matrices M1 through M4, they do have a span. There's stuff in that span. It just so happens that the matrix A we started with wasn't one of the vectors in their span. So that's linear independence and how to check for it. And next we're going to take the idea of linear independence and the prior idea of spanning sets and put them together for one wonderful conclusion.